evening, good morning, good afternoon, in whichever part of country you are. So, wishing you all the greetings of Christmas and the upcoming New Year. And if I am audible, so please comment in the comment section that I am audible. Please type yes if you can hear me, if you can see me. Good evening, everyone. Good morning, good afternoon. All right. So, a very warm welcome to one and all our distinguished guests, our colleagues, dearest students, ladies and gentlemen. And if I'm missing out on anyone, then to all the esteemed participants of this webinar. So, ladies and gentlemen, my name is Anirudh Katyal, and I am privileged to be a part of today's webinar, which is being organized by Celestial Deep Space Communication. My heartfelt gratitude to the team of Celestial for giving me this opportunity to moderate today's session. And Celestial, as all of you know, it envisions itself as an organization of global standing, which fosters development of professionally competent talent. And so it contributes to space programs and missions as well. So with such a vision in the minds of Celestial's team, it has taken another leap in this journey where it is launching a webinar series that is giving us a chance to interact with and, of course, hear from the experts and researchers in the space fraternity. And eventually, this is going to broaden our horizon about deep space communication. So, to add another feather to its hat, Celestial has come up with yet another interesting session of webinar titled as Waves, which you were also having a look at a few minutes back. And today we are here among you with the second part of this workshop, which is going to focus on link budget. Right. So it's going to focus on link budget today. So we are excitedly looking forward to get into some technical calculations and hands-on experience. So all those, maths enthusiasts or all those who have been believing in calculations. So it's today, it is your day to have a hands-on experience and of course, get some number crunching done as we talk about the link budget or the part 2 of this workshop. So before that, I'm delighted to share with you that we had a fabulous response during our first session that was conducted a couple of weeks ago. And not just this, we also received a handful of feedbacks and insights from all across the globe, which we have studied and analyzed carefully here at Celestial. And after this thorough analysis, you shall now experience the enhanced outcome in today's and upcoming webinars. So thank you so much to all our participants, all our followers, everybody who has contributed in making each webinar, each journey more successful, as we come and present to you. Thank you so much to all of you who have joined us back today yet again after the successful organization and the conduct of the first session, which I told you was a couple of weeks ago. So today, I'm sure you're going to experience a phenomenal journey into deep space communication calculations. So yes, focus on the word calculations today. Now, I'm also honored to host today's webinar with the speaker, as always, Mr. Mayank Sharma. So Mr. Mayank, he's the founder and MD of Celestial Deep Space Communication. So he's done his bachelor's in technology in aerospace engineering from University of Petroleum and Energy Studies, Dehradun. Thereafter, he worked as a stress analyst with India's leading tech giant TCS. I know Mayank doesn't want to wait much, and he's somebody who's very humble when anybody introduces him. But Mayank, I'm going to take a couple of minutes of yours to introduce you. So as I was talking about Mayank, after his bachelor's in technology in aerospace engineering, he worked as a stress analyst with India's leading tech giant, that is TCS. Post which he took a giant leap to pursue his master's in space engineering from TU Berlin. Thereafter, while pursuing his master's, he launched a startup by the name Celestial Deep Space Communication. And there you see, Celestial is all live to you. And since then, I would say there has been no looking back, and I'm sure Mayank would second to me on that. So without further ado, I would like to hand over the proceedings to Mr. Mayank. And lastly, I would want to request all of you to be as participative as possible. See, when we talk about calculations, when we talk about numbers, you can't sit with your hands folded or with your mouth shut. You need to talk, you need to participate, you need to have some hands-on experience, you need to make some calculations, make errors, challenge the fraternity which is there at Celestial Space Technology, so that we can get back to you with the best possible answers. And of course, as Mayank is going to take this session, so I'm sure he would love to have a participative audience. So Mayank, let's begin with today's session. And before you get on with the technical calculations, of course I'm very afraid of them, but before you get on to that, so just do let us know that what can we expect out of this session today? What are the learning outcomes, and what are you going to talk about? Because what I know is link budget and its calculations, but I want you to brief our participants about what we should look forward to today.
Yes. So thank you. Thank you for the introduction, which was overly rated, but thank you. Coming back to this point, yeah, today's session is more or less on the technical sides. This is also where I started my journey. I started with this link budget calculation, and they are very, very critical to understand the entire architecture of communications with satellites. And this is why I planned on doing this, because this gave me myself as a holistic view of space communications. And from there on, I started building communication systems and antennas for small satellites. And this is why I wanted to give these students and my colleagues who will be joining a very, very fresh experience into the very easy entry gate for these space communications. Additionally, it took me some months to understand these calculations. This is why I came up with a very short version of tool, so that it takes few minutes for anybody to understand the overall architecture. What took me some weeks and months to do, would now be able to, or this short version of tool would be able to explain them and visualize them within few minutes or maybe half an hour or so. So this was the entire intention of having this session now, to explain this easy barrier or low barrier introduction into the communications, and then help them to use this tool that I have designed now for better understanding and increasing the interest of space enthusiasts into space communications, particularly. But before we go into it, I would also like to introduce, or showcase my team who is working behind. Of course, Anirudh, you are already here. I'm here, but we also have Puneet, who is helping us from the back end. He is. I think he can explain himself better. So Puneet, please introduce yourself here.
Hi, I am Puneet, and I am currently pursuing my MBA, and I'm with Celestial. It's been approximately 6 months above, and I'm working with them in their operations and marketing domain, and hope to see you all take as much opportunity from this webinar as possible. So just be free, reach out to us in the comment section, and feel free to ask questions, and we'll happily answer.
Great.
Good luck.
Yeah, and I also had my colleague Johannes. He was supposed to join, but he is in some other meeting now, so he's not joining. But then this is the team actually who is working behind. So yeah, now Puneet, it's you again back to your seat in the back end.
All right. So thank you
all
so
right.
much
Yeah.
for the introduction to the team as well. And as you spoke about, you taking a lot of weeks and months to understand the calculations. So I would say that this is what every space enthusiast look forwards to when it comes to typical research. And when you talk about communication systems, it's not possible to begin your journey without numbers. So theoretical aspect is one part, but everybody looks forward to making those link budget calculations which are there. Talk about the various parameters such as the frequency, the bandwidth. A lot of parameters are there. So
Yeah.
with that in mind, I would hand over to you now to begin the calculations, and I have my pen as well as the paper on. So I'm looking forward to begin the calculations on my part as well.
Yeah.
And we're looking forward to a very, very enriching session from you. Thank you so much, man. And we'll the audience is free to ask questions. In case if we get some good number of questions, I'm surely going to interrupt you in between so that you can answer our questions and solve our queries as well.
Yes, please do that. I would also invite everybody to be vocal about it. Please comment. And I also have some questions. So I also received this feedback last time that this should be more interactive. So I have created some questions. I also have a small question at the end of this presentation for the students, for the other people who are working on this tool, to actually solve this and get back to me, and I'm happy to discuss. So now actually I can start with my presentation then, on the link budget. So Yeah, so today, basically about link budget. This is basically, as I said, is the basic calculations. Before you start building your hardware, you do these calculations in order to understand what is the requirements you want to give and what is the results you want to obtain. Getting on to the content of this presentation, basically, I would be going into the critical factors for this link budget. What are the assumptions you do? And then later on, I will move into transmission and reception calculations, where I will explain you very briefly about the architecture, antennas, and how the losses happen while the signal is propagating from transmission center to the reception center. Then I will also cover some noise sources and how they are caused during this transmission. And towards the end, I would explain you about the signal to noise ratio. Basically, this is where you get the result of your calculations and you try to understand how much link overlap or what is the strength of the signal that you would receive on the receiver side, and what kind of sensitivity of the receiver you want to have in order to receive all the information effortlessly and errorlessly. And towards the end is the summary sheet, which is basically also the tool that I have designed for all the participants here. And then lastly is the case study, which is a question I would leave every participant here to follow up with in the later on. So what is budget, first of all? So somebody asked me, budget means giving out groceries, money. So I took it from there only. So yes, shopping budget, right? And then you have basically an estimates of what you want to buy, how much money you have. What you also have these sections in the budget, basically, where you want to spend some percentage on groceries, some percentage on clothing, some percentage on different sections. Similarly is the link budget. Only problem is, or only difference is, the link budget is basically an estimation of the signals, and here you are spending on the losses that happen on its way when the signal is transmitted, and you are basically trying to estimate how much power you have to spend, how much money you have to give, how much power you have to spend into this link budget in order to have this fully and successful end-to-end communication architecture working. The critical factors that we take into picture is available power on the ground station. So how much is the power of the ground station is. More the power of the ground station, stronger the signal it can send, and weaker the signal it can receive. Similarly, on the other side, available power on the satellite, because satellites are generally low powered systems. So they basically also are very critical. Basically, this is also one of the limiting factors of a link budget, because your satellite is limited on power. And then you have radiative power, which is basically the overall aggregate of the gain and the strength of the power input that you give, the losses that happen in the electronics, and the antenna, which gives strength and directivity to the signal overall. And towards downward is then basically the sensitivity of receiver. Once your signal is transmitted and your receiver receives the signal is so weak, so small, that your receiver has to be very sensitive to actually sense this signal and deduce the useful information out of this signal once it is received. And this is what makes signal to noise ratio, SNR, of the receiver, which also basically is how much signal is received out of the noise. And noise I will cover in the next slides, where is sources and why it is caused. Then other critical factors are basically what type of antennas you are taking. Is it omnidirectional antenna? Is it directional antenna? And what is the gain? What is the performance of this antenna, basically? And for that, you generally refer to some kind of data sheets off the shelf available antennas, and you use them in your link budget calculation to have some realistic approach of the signal you are trying to evaluate. And then towards the last is longitude and latitude of the ground station. These are particularly important because you want to evaluate to the satellite where, in which orbit the satellite is moving, what is your longitude and latitude of the ground station, and how much window you will get to communicate, the feasible window, because you probably wouldn't be able to communicate below 10 degree because atmosphere is thick, so there is a limitations around this atmosphere. So longitudes and latitudes of ground station are very important then. So coming to the transmission and reception. Basically, an RF link is a link between two locations where you are sending a wireless information from transmission to reception. And this transfers generally in electromagnetic waves or millimeter waves. And then there is an intensity of this signal, which actually depends on the square root of the distance between these two. More is the distance, weaker would be the signal that would be achieved because of the absorption in the atmosphere. These things I will also cover in the next slides. There are two keywords to this. One is uplink, other one is downlink, and this is how link budget is also calculated. This is calculated in uplink link margins and downlink link margins. The uplink is basically when your ground station is sending a command to your satellite where it is asking it to switch off some system, do some orbit maneuvers, some kind of command that you are sending from your ground station to the satellite becomes your uplink because it is going up. And then downlink is when your satellite reacts to these commands, or basically it sends out what is the battery power left, or what is the we call it housekeeping data, or what is the payload. If you have a camera, some images transmitted back to the ground station. So basically this becomes your downlink, so all the data that comes from the satellite to the ground station. This is basically I wanted to give you a schematic idea about how link works. So coming to this left hand side, and I hope you can see my laser pointer here. So I would cover this part first, the uplink part. So just to give you an idea, when ground station sends a signal to satellite becomes an uplink. When satellite sends it to ground station becomes a downlink. So when you are sending this uplink, you are basically having a ground station which is having power amplifier, which is having this powerful electronics and lot of power input. Their signal is really high, but then it is transmitted, and when it is transmitted, based on the electronic and losses that it suffers, your signal tends to go down. But as it reaches towards this antenna part, because antenna has a gain itself, antenna itself strengthens the signal, also directs it in a particular direction, your signal goes up considerably. And then when it is up, it is transmitted into the air. So this area or this region is the atmosphere. Now here maximum losses happen because of absorption, because of scattering, because of reflections, refractions, various phenomena that happen in the atmosphere. This is the power where it goes considerably down, and over here the receiver antenna receives it. And this receiver antenna, this is why ground station antennas are very large, because they want to absorb maximum flux density or power density of the signal that is coming towards them. And once they absorb this, since antennas are also having gain, so they also act as kind of an amplifier. So they basically give this strength to the signal, so that the electronics behind is able to sense this signal out of all the noise that it will absorb. Because mind you, when this antenna is receiving the signal, it is also receiving very spurious signals which are not of any value to this antenna or to this system, but it is able to receive this because of its aperture, because it's receiving all the noises. And this is what happens over here, and this signal is strengthened, and the electronics is basically able to deduce the information out of the carrier wave in this area. And just a vice versa process happens here also. Only problem is your satellite is lower on the power budget. You cannot have such high power budgets. So this is why this starts very low already, and this is why you need to have a very high efficient antenna on the satellite in order to push this as up as you can, because these losses will damage your signal a lot. And this is why the ground station antennas are made bigger, so that they can sense the minimum of these, and so that they can give this ground station the maximum possibility to understand this information once the signal is received from this signal from the satellite is received by the ground station itself. Okay, so moving on to the next. Yes, so moving on to the next slide, I just have one question for the audience, because I wanted to make it interactive. So I will explain you, I will give you the answer to this, but just out of curiosity also, I wanted to understand, what do you think is the highest or majorly used frequency with small satellite communication? And the options are A, B, C, D. So I invite you to comment A, B, C, or D in the comment section below, and let me know what you think about this. A option is ultra high frequency, which is 300 to 3 gigahertz, mostly used by amateur radios, students, academic. And then there is B, which is S band. It's higher upper ultra high frequency, and this is from 2 to 4 gigahertz, and this is used by majorly industry or also amateur radio license. And then there is C, which is X band, which is from 5.2 to 10.9 gigahertz, and this is majorly used by high throughput satellites or CubeSats basically, and is more focused by industry. And then D is don't know. I give you roughly 30 seconds to answer this, and then I will move on to the answer of this. So yeah, please go for it.
So we can see our audience has been very active and they have already started answering. So we have the answer as B, we have the answer as X band also, B and C for military. All right, we have the answer coming as C also. So we have a new option coming up. But as of now, I can see that most of the people they are commenting B as the option which they feel is correct, which is the S band. So just stay tuned. Our
Yeah.
professor for today is soon going to come out with the answer to this question.
Yeah.
Well, I guess we are just through with the. All right. So last 5 seconds in case if somebody has left out. If somebody is left out, so quickly key in your answer, and then we will have the final answer coming from our professor today.
All right. So
Man.
yeah, maybe I can move on, right? Okay. So thank you for your response, actually. But to your surprise, actually, A is the answer, ultra high frequency. I tell you why, actually. So just let me zoom it a little bit in. So over here, ultra high frequencies. This is basically data from nanosats.eu, and this graph basically shows roughly 1,300 or 1,350 satellites out of 2,000 satellites launched up until now. These are specifically for CubeSats or small satellites. They are using UHF frequency. This is basically because UHF frequency is majorly used by students, amateur radios, and you don't need particularly high requirement of reserving these frequencies. You just need to have a radio amateur license and you can use these frequencies. Whereas for S and X band, you mostly need to go for reserve. These are also commercial frequencies working in this region. And now, since the industry is moving into small satellite industry, we are expecting actually a high growth to be seen in this S band and X band frequencies. And of course, UHF will keep on rising, but we also see or expect a high growth in S and X band frequencies. So yeah, the data was from nanosat.eu, actually. But coming on to our point now, the frequencies. So this is the most important part of a link budget. When you start with a link budget, you need to know what frequency you want to work on. There are various parameters that you can decide this on based on what is the data rate you want. So higher the frequency, more is the data rate, more is the bandwidth you can attain. Lower is the frequency, basically you can get telemetry data, other small datas, and not very high datas in that scenario. But important is you decide on the data. And then what you want to get out of this is path losses, because there are some path losses that will happen on the frequency. So higher the frequency, more will be the path losses that will be suffered by your link budget. And the explanation about this is basically when this is traveling, and there is basically power reduction. The power density of the signal, it goes down when it is traveling through the space. And this is the reason you have to be very careful about selecting the frequencies. There are various reasons of this power losses, which is because of reflection, refraction, scattering, absorption, and based of this, there is also standard available graphs where you can understand how different layers of the atmosphere and how different gases in the atmosphere absorb different frequencies at a different rate. So that is basically the reason why this happens. The calculation of losses depends on this free space attenuation formula, where you are able to understand how, based on the wavelength of the frequency and the slant range can be evaluated based on the orbit you are using your satellite at. So your satellite will have an orbit which will have a minimum height and a maximum height. Based on apogee and perigee of the orbit, you can evaluate the slant height d, and based on the frequency you select, you can evaluate the wavelength of the frequency. And then based on this formula, you can evaluate the losses it will suffer based on the evaluation of your ground station and the satellite, where d is really high than lambda for obvious, of course, for the obvious reasons. And then, as I said, the losses which happen in more detail, if we go, there would be absorption losses because of ionospheric effect, atmospheric effect, and precipitations. And there is also cloud attenuation, basically the absorption of signals due to water vapors. And then there is something called polarization coupling, which I will also take on in the next slides. But basically, your signal is sent in a particular manner, in a particular pattern, and if your receiving antenna does not resonate with this pattern, it would miss most of the information. So your transmission and reception antenna has to be polarized in a same polarization pattern to send and receive and have this overlap, else there would be mismatch of polarization and losses would occur. And then there is an effect of wave interference. So basically there are other waves going around, because your ground station is in a locality, or even if it is remote, there are many signals which are being transmitted throughout the globe, and your antenna would be able to take lot of signals or receive lot of signals, because it doesn't know which to receive and which not to receive. And hence there will be lot of interferences because of overlap in bandwidths, because as you saw, there is roughly 1300 satellites working on UHF frequency. Now all of these satellites are transmitting, so there is high chance of interferences in these frequencies, which are very popular and very commonly used. And then there is line of sight loss, basically when there is something comes in between your satellite. A good example would be when your satellite is, for example, a moon mission. When the satellite goes behind the moon, you cannot see your satellite, and your ground station cannot see your satellite. You have no communication. This could also be a case when there is a tall building close to your ground station, and you cannot see because building is blocking the signal to the line of sight to the satellite. Now, the considerations. Basically, we are using conversion formulas. First of all, this is a consideration. So generally, power is estimated in watts, milliwatts. There is voltage concepts and there is voltage units being used, but we use decibels. Now, this is just for my understanding also. Is there anybody who can reason out why we use decibels in this? I give you 30 seconds. If somebody knows, please comment this and let me know why we use decibels and not watts and milliwatts in the calculations. And this is also the unit of sound, decibels. So why do we use decibels if we have watts and milliwatts? So yeah, I'll wait for 30 seconds.
Come on, participants, we need answers. So Mayank has posted a question and we need to be spot on with the answers. Any guesses, any random guesses coming up? All right, so we have an answer which says that communication involves sound communication, which means decibels. So is that one of the reasons? And somebody is also saying that we cannot represent in milliwatts. So could that also be the reason? But yeah, I guess the question is why we can't represent in uh, milliwatts.
So answer is pretty close actually. So really, really nice answers. Actually, it's pretty close. We use decibels because sometimes when we are doing this evaluation, our calculations tends to go like 0.001 millivolt. The number is really small. And so just to give you a one-line answer, this is a shorthand unit to be used for milliwatts and watts. And this is why we use it. And I have given some conversion formulas, but in order to have easy calculation and understandings, we use decibels. But this can very easily be used in milliwatts also and watts also. Only then your units or your figures will be in 10 to the power minus somethings, which is not very easy or not very comfortable to work with. Okay, then moving on to antennas now. Directional and omnidirectional. Right now, we are on the right hand side, I have shown is a patch antenna. This is developed by Celestial. We demonstrated this antenna during an analog mission with Swiss Space Center under ESA Lab initiatives called Igluna 2020. You should check this out. This is an analog mission where student teams, they demonstrate moon habitat and they bring out the technologies what would be used by future astronauts on moon or lunar surface. And we demonstrated an antenna and a communication system for such habitat. But coming to the link budget now, yes, when you start with link budget, this is my advice to you. Please be as realistic as possible. And for that, please try to go into the internet and try to download these data sheets of antennas, of electronic components, low noise amplifiers, power amplifiers, and try to evaluate based on the values you get out of these. So this is why data sheet comparison is very critical for something that you want to design and be realistic about. So here brings me to my next question actually. So don't worry, there are not many questions, but just three questions. So this is the second question now. Please do answer. What according to you is the function of an antenna now? Because I have answer on the next slide. So A, is it there for transmission and reception? B, is it there to direct the signal? C, is it both transmission, reception, and directing the signal? And D, none of the above. So Please take 30 seconds again and just quickly type A, B, C, and D.
So before you could finish the question, we started getting answers. So we have C, A, and then somebody again saying C. So most of the people going for C as the option, which includes both A as well as B, but we are still waiting. So we have still 15 seconds if anybody wants to give another try. So majority of the participants, oh, all right. So we have a mix now. So it's 50% to A and 50% to C.
Okay.
So
Yeah, maybe I can move on now. So yes, it's actually the C. We actually direct the signal also, and we also transmit and receive the signal with antennas. Basically, an antenna doesn't create any power. It only concentrates the power it is being given, and it transmits into a particular direction. This becomes a directional antenna. If it is omnidirectional antenna, that it will direct in all the direction. So considering omnidirectional antenna, yes, A would be the right because it's not directing in a particular way. But considering directional antenna, then C becomes, it also directs and receives in sync. And it acts as a sort of mirror, reflecting the light it is receiving from the bulb and directing it back. On the last part, basically, yes, then antenna is a passive component because it's not actively generating power, and it is transforming the energy which is created by the communication system or the oscillators, local oscillators, and the back end of the system. And therefore, it is also for transmission and reception of the signal itself. Coming to the radio noise, now this is where things starts to get tricky. Basically, when the signal is transmitted into the atmosphere, then there are atmospheric events which are going on. There is also radiations from the local mobile towers, from the cell phones, from other equipments around, which also cause interferences. And then the radiation from the atmosphere gases, basically, which I was also telling, there is non-homogeneous layering of the atmosphere. Then there is water vapors, there is active or active oxygen particles, which is basically our ionospheric layers, which are responsible for the absorption, reflection, and degradation of these signals. And of course there is physical obstructions, which I also explained previously. But then there is also something called deep space cosmic radiations, where there are celestial bodies which are radiating microwaves into the atmosphere, and this is also something which is received by our antennas, and they are also acting as a noise source. Noise basically is also termed into called the noise temperature, which means any vibration, unnecessary vibration in the atmosphere, or temperature is the unit of kinetic energy of the molecules. So any unwanted vibrations in the molecules results into these noises, which is also termed as temperature. And there could be temperature from the system, temperature from the sky, we call it sky temperature, and system temperature. This is what actually adds on to more unwanted frequencies, more unwanted vibrations, and signal which is received as a form of a wave is attenuated, is also damaged, and the quality of signal received also goes down. Even after receiving a good quality of signal, this could happen if your receiver is heated up, is at high temperature. And then which is also called system losses, which is basically called system noise at the end, last bullet point you see. And then there is impedance loss. So I also suggest when you look out for different components in data sheets, please verify that you focus on 50 ohm. This is a resistance that is offered by and majorly standard that is offered by RF components, radio frequency components. And you need to match this from component to component, and also from the circuit level. For example, through the circuit RF front end circuits, you need to match this 50 ohm, because if there is no match, then there would be a loss of information, which would result in a standing wave, which means your signal would backfire and could also damage your electronics on the circuit, because your resistance, which is ahead or into the next succeeding component, does not match with the resistance of the preceding component. And then there is insertion loss. When you look at the data sheets, you will also find insertion loss, and you need to look at the frequency you want to work on, and opposite to that frequency there would be an insertion loss value, and try to have minimum of insertion loss, because this is basically the insertion losses or losses due to imperfect circuit wiring inside the ICs or inside the components itself. So insertion loss again adds on to the degradation of the signal which you are transmitting out. Now coming to the antenna pointing losses. So when you are having a ground station at the looking towards your satellite, and your satellite antenna looking towards your ground station, now there is very less possibility that your both antennas align on their axis to communicate. There could be a little bit of mismatch very easily. Now this is where you have to refer to your data sheet of the antennas again, where you will look into the view angle of your antenna, and you will set a limit to what your link budget is able to sustain if there is a mismatch, where I have represented on the diagram as theta1 and theta2. You will be able to evaluate if this is theta1, how much of the deviation your system could bear from the mean lobe or main lobe of the antenna in order to still receive a valuable information. And same goes for your satellite. The pointing errors basically are very critical, because if your antenna or ground station is pointing 90 degree up, directly up towards the satellite as the azimuth angle, and then your satellite is pointing in some other direction, this could even result in no signal at all, because your antennas do not look or do not see each other. This is the same concept as your eyes. You are looking in one direction, you can only see that side, you cannot see what is happening behind you. Same is with antennas. The directional antenna, in the direction they are looking at, they will only be able to transmit and receive in that direction. They won't be able to transmit more than that direction, and this value will be given to you through the data sheets of this. And please be careful when you select an antenna, please try to use the same data sheet for antenna pointing losses, for gain evaluations of the antenna, and for overall antenna architecture. Do not mix the data sheets, because if you do that, then you will end up with some kind of antenna that might not even exist to be used for your network architecture. Coming to the polarization now. So when the signal is transmitted, the signal may be transmitted in three type of patterns. One is linear polarization, circular polarization, and elliptical polarization. I'm sorry. So when you are transmitting a signal and your antenna is transmitting this either parallel to the horizon or perpendicular to the horizon, the electronic E field, which we call, so electronic field or electrical field, which is transmitted out of the antenna, if this is either parallel or horizontal to the horizon of the antenna, then this results into a vertical and horizontal polarization respectively. And there are two components of antenna. One is, so I would use a keyword here, it's called TM01 and TM10 mode basically. So it's the basically, let's say, 1 and 2 mode of the antenna. One is horizontal mode, other one is vertical mode. The antenna I was showing you, it has both the modes in it. So based on the input of the power you give to this antenna, you might even be able to distribute the power equally to these two modes. If you are able to do that, then your signal would travel in a circular fashion, which will give you a circular polarization, because both modes are active now, rather than one mode, which was the case in linear polarization. Now, if your signal travels in a clockwise direction, then this becomes right-hand circular polarized wave pattern. And then your receiver antenna should also have right-hand circular polarized pattern to receive the same signal. On the other hand, if your signal travels left-hand circle polarized, then this will anti-clockwise, then this becomes left-hand circle polarized, and this is also the condition. Then your antenna on the receiver side should be able to resonate with this polarization. This happens because your power is getting distributed equally in both the modes. But what if one of the mode gets a little bit higher power, other gets a little bit smaller? This will result into an elliptical polarization, where you will have one mode is resonating more, other one less. So it becomes rather than a circle, it becomes an ellipse, where major axis would be resonated with the mode which is having more power absorption than the other mode. And when you have this kind of polarization, elliptical polarization, there could be polarization mismatches, because your elliptical polarization could be 0 degree, 45 degree, or 90 degree. So your ellipse could be either vertical, horizontal, or in the middle. And then your receiver antenna has to have same kind, else if there is a mismatch, there could be a loss of power up to 30 dB, which means half of the power, almost half of the power could get lost if your polarizations are not matched. There is more information on this. I asked or I suggest you to actually look up some good research papers on this, and you will be able to understand this concept very well over there. Then comes basically towards the last part is the modulation schemes. So when a signal is generated, it is very weak. In order to send this over thousands of kilometers, you need to put a carrier wave onto this, which means a much higher frequency wave, which will able to carry this signal, weak signal, from one point to the another. And this is what happens when you are putting a carrier wave and you try to superimpose a signal generated to a carrier wave, and this is where modulation comes into picture. The process of superimposing these two is basically called modulation, and this could occur in binary phase shift keying, quadrature phase shift keying. There are n number of modulation schemes. I won't go into detail because I do not have much time. But when you have these modulation schemes, then you also need to have same kind of demodulator at the other side in order to demodulate the carrier wave that is received and extract the information out of it. Mind you, when you are working with the modulation scheme, there is a basic threshold of this modulation that you need to overcome, and when you do that, only then your signal would be able to retrieve its information. And this is what happens at demodulation. A demodulator has to overcome or has to compensate for some amount of dBs, which I will also cover in next slide, which is responsible or required to remove the information from the carrier wave once it is received on the receiving end. Coming to the receiver sensitivity, which is basically once you have all of this, then there is something called figure of merit, which is basically the ratio of gain to the system temperature of the receiver itself. Once you have this figure of merit, this gives you the efficiency or the performance of the receiver, and this also helps you to actually make an estimate of the power noise spectral density, and to get ultimately EB over N naught, which is basically your signal to noise ratio. Here in this formula, this is basically Boltzmann's constant. Then this is the temperature of the system itself, gain, and then this is the power which is at the receiver end. Once you have this, you will be able to get this PR over N naught value, which would help you to evaluate this signal to noise ratio, EB over N naught. And this is what I was calling having a threshold. If you are using this EB over N naught, this is inversely proportional to the bit rate, which is the data rate that you will be sending out. And this is what is called energy spectral bit per bit, energy per bit to the noise spectrum density. So for example, if I am using phase shift keying modulation scheme, I would have to spend 9.5 dB of energy for a minimum error. This is called bit error rate for 10 to the power minus 5, which means, okay, just quickly explaining BER, which means you are supposed to have 1 bit error in 10 to the power 5 bits, basically. So that is the error or accuracy of the signal needed once you are transmitting the signal. And this is the energy that you will have to spend at the receiver end once you receive the signal in order to extract the information. And this is what it is written here. The sensitivity of the receiver is noise plus this dB, because this is also spent out. Coming to the last part now, link budget. Basically, this is the overall calculation where you have power transmitted. So it's the power received is what we want to understand. So power transmitted to the gain of the antenna at the transmission end, gain of the receiver at transmission end. This all can be calculated from the data sheets. This you will have to evaluate how much power you want to give at the TX, and then you have losses at transmission end because of insertion losses, because of components that you are putting in. So there are some losses at the TX end, line losses we can call it, and then there is losses because of because of frequency free space losses. So this is when the signal is transmitted into the atmosphere, and all the losses of absorption and other scattering and ionospheric losses occur. So this becomes losses in the free space. And then this is polarization losses that happens on that side. And then this is losses on the receiver side. Actually, this should be minus here. It should be subtracted. But this is losses on the receiver end. And basically, if you are able to evaluate this and you have some kind of power, Then based on this, you calculate the signal to noise ratio, because this is PRX I was using in the previous formula, which was here PR. So coming to that, and once you have this, you are able to calculate signal to noise ratio, and from that you will find the link margin based on the link you are receiving, and the EB over N naught you subtract out of it, and if you are have a positive number, then you have a link margin which is positive, which is link closes, and then you have a link margin of 15 dB, for example, which means your system can withstand an additional damage to the signal of 15 dB, which is quite high. We never go for 15 dBs. We generally keep ourselves to 1 to 3 dB in order to avoid any over engineering efforts, and also keep ourselves economical and get the best performance, because you will also be able to evaluate and get your information just based on the 3 dB link margin. Also, you don't need 15 dB link margin. So just to save all the over engineering efforts, we try to be as close to zero as possible. Then there is one last question I want to ask. So why do you think small satellites are important now? As I said, now industry is moving to small satellites. Why do you think these small satellites are gaining importance? Basically, is it lowering the space mission threshold? Basically, the cost and manufacturing efforts is lower in small satellites, or basically for deep space missions, because we want to send smaller satellites out there, or do we want to do sustainable space, because if we have smaller satellite, then there is less space debris. Smaller satellite means more satellites can be up there. So is it that, or there is some other reason and it's none of the above? So yeah, please take 30 seconds and try to let me know.
For the answers, so we have B coming as the answers so far, and we are waiting for others also to key in their answers. So how many of you think A is the answer? Key in your answers in the chat section. A as the answer. Not many going for it. And we have B as the answer. So we have a majority of the audience opting for B as the answer.
Okay.
Nobody going for C and D at the moment. So B stands the majority of the participants giving that as the answer. So Mayank, what's the correct answer here?
All right. So yeah, I don't have any other slides to justify this, but actually the answer is A. The reason is, if you want to go for sustainable space missions, then you need to have a deorbiting mechanism. You want to remove satellites from this. You don't want to have a small satellites up there. Even small satellites are space debris. Space debris could be as small as millimeters. So small satellites are no solution for space debris as far as satellites are concerned. But deorbiting mechanism is required. For deep space missions, you are actually in hundreds and thousands of kilometers away from Earth. So you need high power to transmit the signal. You cannot send small satellite to do deep space missions, because satellite is low powered. It cannot transmit the signal. You won't be able to do a deep space mission with a small satellite. So this leaves with the answer A, because small satellite needs less effort. Additionally, small satellites have set up a standard in the industry where you can just buy a satellite off the shelf, put your system in, and launch it. Bigger satellites, they don't have a standard design. Small satellites, CubeSats, for example, they have a standard design. This lowers the manufacturing cost, because you can manufacture them in bulk and start selling. And secondly, this also makes standard for different subsystems to be implemented into the satellite. So this lowers the threshold, and this is why I said small satellites are used by students. Small satellites are used by radio amateurs, and this is why UHF frequency is really highly used by small satellites at this time, which we also saw in the graph previously. All right, good enough. Then, yeah, this is the question, but I will do this later on. I have actually another slide over here. Let me check, where is that? I wanted to show you the tool now. Yeah, so yes, I wanted to show you the tools, the one which you would be using. So let's go to the tool first. So yeah, for the this is basically the summary sheet, and on the right hand side you see is a quick Excel, which is also the tool to evaluate everything. So all that I explained is the point here, but for that, let me share my screen again, and let me just share my screen and share the tool with you guys, so that we can actually share the tool itself with you. So the tool now, let me just give me 1 minute actually. I'll share the screen now again. Okay, is the tool visible, right? Anirudh, the tool is visible.
Mayank, I guess you'll have to reshare your screen once again
Okay.
because we are not able to see the tool as of now, or probably there's a little lag.
Okay. Yeah, let me see that. Now it should be up there now. All right.
Yes, it is visible now.
Okay, good enough. So now this is the tool that I designed. And first of all, before we move, I would say these are various groups you can contact us with. So LinkedIn, YouTube, Facebook, and then there is also a community that we have designed. So LinkedIn community, you can join this as well. But coming to the link budget now. So this is just one tool that I designed. I kept this name, some mission name that you want to keep. But then majorly what you want to do is you want to work on these green boxes. This is where you will give what is the transmitted power, what is the line losses. This is what I was also calling system losses, which happens due to insertion losses of the components, due to line losses, due to the impedance losses if you have impedance mismatch between. So this is the transmission losses which are evaluated, and then based on the antenna data sheet you will give an input of the gain. So for that, please enter your first of all the values for your operating frequency. What is your altitude that you want to target your space mission? Body means the Earth's radius or moon radius, for example, whatever you want to enter. And elevation angle is basically what is the minimum angle you want to work with. And then based on this, you will be able to evaluate total radiated power that is transmitted by your signal or by your system towards the sky, towards your receiver. And based on that, you will also have to then evaluate what is the pointing losses you want to work on, or what is the pointing losses your link budget can sustain. Mind you, pointing losses, they basically go really fast when you are doing this, and for that you have to just evaluate basically a very small evaluation. I would say this general value for pointing losses should be kept within 5 dBs. Do not go beyond that. This then already is too damaging. Already 3 dB is too damaging. But if you are able to close this to 3 dB or 5 dB over here, then this is good. But over here, when you see this as 0.2 or 0.1, this is basically a point or pointing loss or pointing error of 1 degree in the view angle of the antenna. So we can only shift 1 degree our angle, else we will lose our signal with that. And then based on this, slant height is evaluated, which comes from your orbits. And then we evaluate the free space losses, which is also I explained you how free space losses happen. And then there is atmosphere losses and polarization losses. So atmosphere losses, I have given this table. You can refer this, and based on your elevation angle that you want to communicate with, you can put some atmospheric losses value in this. For example, I have kept elevation angle as 20 degree here, and I evaluated this to be roughly 1.1, roughly close to 10. But then polarization loss should come from this table, which polarization loss is again something very similar to antenna pointing losses, only polarization mismatch happens, and this cannot go beyond 3 dBs. And I suggest you do some little bit of research on this and find what polarization loss you would suffer. But as a hint to you, polarization loss is assumed between 0.1 to 0.3, just a conservative value I have given. So in case you are not doing this Google research and you just want to use it, you can use this as polarization loss, because this is an estimate. Link budget is an estimate, so you are estimating few things. Everything won't be accurate in the first go, but this would be a really good estimate to give you the direction and want to improve individual components later on. Okay, and then on the receiver side, again, you should put same kind of pointing losses. Almost same kind of pointing losses can go on the receiver end also. And then receiver antenna gain would be just the same antenna gains, only reversed. Then 8.3 is on the downlink side, because now it becomes a receiver, and transmission antenna becomes a receiver over here. So this is just reversed. and there is a difference because of the frequencies that you would work differently on. And then there is again transmission line losses on the receiver side now, because you again, when you receive, there are electronic components on the receiver side. So there would be low noise amplifiers, there would be insertion losses because of filters and other electronic components, and so this would be basically your transmission line losses that you will have to account for. And then there is overall system noise. System noise is basically an evaluation of basically an evaluation of the temperature that your system would experience based on the unnecessary radio noises from the celestial bodies, based on the temperature of the system itself. So I actually suggest you that you can use, so this is a formula to evaluate the system noise. This is basically which includes temperature of sky, temperature of the system is evaluated, temperature of sky is included, overall temperature, this is temperature of low noise amplifier, then there is temperature of temperature to gain ratio of low noise amplifier to the second stage. So this is basically an overall formula that you can use, but to be conservative, I have already given you, if you are working on a ground segment, you can keep this 600 kelvins to be conservative, and for the space segment you can keep this as 300 kelvin to be conservative in your approach. And then based on that, once you have this system noise temperature, then you have to decide what is the data rate you want to work on. So this is where you want to put 1 megabits, or for this case this is just a try, 1 megabit I have put, but you can also use, for example, 1 kilobits or 2 kilobits, which is generally the case with the CubeSats or small satellites. And then your signal would improve drastically because you have less data to be transmitted. And lastly, EB over N naught threshold, which is based on the modulation. And this is a scheme which also comes with convolution code. I did not cover convolution codes in my presentation today because of the time lag. But EB over N naught you will find easily with a lot of research papers, and I strongly suggest you to go into that and look for what is the threshold that you can put in there. And once you do this, then you will be able to put a limit on this threshold. And I said you have required EB over N naught as 7, and then EB over threshold, that's something you pay out, and then you have a link margin of something which is a difference of these two. So this is basically link margin. And you want to have a link margin above 0 every time, because that means link closes and you will be able to have a communication between the 2 points you are trying to evaluate. So this is a very short version of a link budget, very quick version of link budget to do this evaluation and understand these things very quickly. And there are bigger link budgets available online. I also suggest you can go into that. They are just more overwhelming to start. They are more cumbersome, and they have many sheets under it. Each and every individual component over here, as I have put on the table, has individual sheets, so they go in depth and take further details into this. So I also invite you to do that. And this is also what I did, and took me some weeks and months to understand those link budgets. And this is a tool if you want to just start analyzing this on a quickly manner, and very less time. You want to just understand link budgets at the starting, and then develop your interest and move into deeper or more lengthy link budgets. So yeah, that would be the presentation side. And just one last thing I want to show is basically the question that I would like to leave it for you. If you want to work on this tool, and if you want to show or get back to me with your calculations, I would be happy to answer this also. And so that's basically what I wanted to show. Just give me 1 minute. Let me share my screen back with that question I wanted to share with you. 1 second. So okay, so can you see the screen now?
Not yet, man.
Okay, it's coming up now. Now it should be up.
Yes, we can see it now.
Okay, so yeah, this is the question basically. So I designed a very pseudo mission with all the details in there which you might need. So yeah, I will leave this for some time on the screen, and you are more than welcome to ask me questions if you want. And please note down this values, take a snapshot if you want, and yeah, get back to me, and I would like to, or would be happy to actually um, reply to you, maybe help you out, or maybe even learn from you guys. So yeah, that's actually very quickly what I
We
wanted to present today.
have our participants team asking for the tool file as well. So if you could probably throw light as to how they can access the tool file as well.
Yes. So yeah, tools. We will be sending out a follow-up mail, and I will try to attach this already, or I will provide you the link to download this file when you want to work on it. So we will follow up either today or tomorrow with a mail, also for the feedback. So it would be really nice if you give feedback also, and you can then do this work on this tool later on.
All right, so we give the audience a little time to probably note down the figures and the characteristics and the values which are there on the screen. Alternatively, you can also take the snapshots of this information which is right there on your screen. So with this, I guess we have concluded the session, or do you have anything else to share, well, Mayank? And then probably
Um,
question answer if there are any
Yeah,
doubts.
if there is some question anybody has, please let me know. Other than that, I don't have anything else to share. I'm happy, and thank you for being here. And yeah, that's actually from my side. So maybe we can wait for 1 minute or two if somebody has a question, something. Yeah.
All right, so we have the open house question and answer round now. So in case if you have any questions, do post those questions in the chat section so that we can bring it up and Mayank can share the answers for those questions with us. So, right. So, Mayank, there's this question about the position of the ground station. So, is this related to the question that you have shared? Is it the ground station position which is required?
So yeah, I haven't shared the ground station position here because this is a pseudo one, and so basically, ground station position is more or less important for the elevation angle when your ground station wants to look at a satellite. So basically, that is what is important. It is for, and I have given you the target orbits, so 300 and 450 kilometers. So take it as a lower point and higher point, and you will be able to evaluate slant range, and based on that slant range, you can set an elevation angle by yourself, 10-degree or 20-degree, and for every elevation angle in the tool you will find atmospheric losses, and this will solve your problem for the ground station position. Other than that, ground station position won't be required particularly into this.
All right.
Yeah.
So, any other questions from any of our participants as we close out on today's session, and we look forward to the next session, which is soon going to be telecasted for all of you. So, in case if you have any other questions, please feel free to type in the comment section. So, we have another question which says that how to set the EB by not required for link budget calculation in your tool. So, Mayank, how can this be set in the tool?
Yeah. So the EB by N naught value is basically the required threshold value that you need to have in order to reduce the signal from the carrier wave. Now this EB over N naught value depends on the modulation and demodulation, and the technique that you use. Now, because of the time, I could not cover the modulation schemes in detail and the um, forward error correction schemes. So these two actually they combine to form this EB over N naught required value. And I strongly suggest you can look up for some research papers where you will find this. But for example, as I have covered in one of my slides, for phase shift keying, it is roughly 9.5 dBs. So this is how you can actually evaluate. There is also a good link budget from Jan King, JANKING. Maybe I can put, or I can share a link to that. You guys can actually look that up. And this is a detailed link budget, which also I worked on, and this would take a lot of time to basically took me a lot of time, might not take so much time from you. So this is the link I posted on the comment section. I think you should be able to see this, but you can also work on this spreadsheet, and you will be able to see various ep over n naught values for different modulation schemes. This will also help you in evaluating those values. I think maybe this would already be an answer for this.
Yes, so I guess the participants have already received the link posted by you. Any
Okay.
other queries or concerns? Of course, as Mayank said, that we are going to share out the feedback form as well. So you can
Yeah.
also type in your concerns there in case if you want to make this workshop better in future, or you have any other questions which are left unaddressed. So
Yeah.
yes, that's it for today. And we had quite an enriching session in terms of the link budget calculations, and of course the tool which was shared with us, which gives us an insight into how the calculations vary depending on the various parameters and the characteristics that we make changes into. So and as you can see on your screens as well, that how you can stay connected with us. So you can expect the third part of this workshop coming up to you on 13th of January 2021. And of course, do provide us with your valuable feedback and insights in the follow-up email, which is going to be sent to you, the follow-up survey, which will be shared with you. And of course, you can always join the LinkedIn group, which is right there on your screen, New Space Communication LinkedIn group. I would request all of you to follow that as well, so that you can get the latest updates from the team of Celestial back there. So that's it, and thank you so much for being such a patient audience, for participating and giving answers to the questions which were being asked during the course of the session, and also asking the questions in the towards the end of the webinar in order to get your doubts clarified. And yes, as I said, that in case if you still have any other doubts or concerns which are unaddressed, please get in touch with us through the various platforms that we have already shared with you. Thank you so much, and looking forward to connect with you in future as well. Thank you
Yep.
so much,
Thank
Mayank,
you.
for
No,
joining
thank you.
us and conducting this beautiful session. And we look forward to many more sessions from you in future as well.
Yes, thank you very much. See you. Thank you for everyone to join. Thank you.